Hello, welcome to my game that is in fact a blatant ripoff of a very popular game called Settlers of Catan. Many of you have probably not played this game because no one called me out on it today except Mr. Cha, so score me. The way this game works is you get to choose a tile or a location that you think is going to have the best resources for you. And you are looking to end up in the best situation at the end of the game, which I represented here by getting the most gold. But as we played today, people found that some of them just weren't lucky. Sitting on this place where you should be getting iron, but you have to roll an 11 across 2 dice, just wasn't happening much. And we used this to talk about the fact that sometimes a game that looks like all the outcomes are equally likely, because we're rolling dice. Those are, 1 out of 6, right? In fact, don't have equally likely outcomes, and in fact, it ends up not being a fair game. The first person who went gets to choose, and so theoretically they could choose a place that would give them a better chance of winning than other folks. So first we played, and each person chose 2 places they wanted to claim resources for. And people started noticing this inequity, that some people were getting their gold a lot more often than other people. I asked us to be more precise then and actually do some experimental data. So people played for about 3 minutes longer and they recorded what they found. And this is just an example, but this is what I saw from a lot of people. If we started at 1 and we were going up to 13, nothing was at 1, because if you roll 2 dice and add them together, you can't get 1. 1 plus 1 would be the lowest, that's 2. Can't get 13, because the highest you can get is 6 and 6, or 12. And there was sometimes a 1 or a 12 that was rolled, but we ended up with a lot more of our middle numbers being rolled. And so it looked like, for some reason, these middle numbers were better. You had better odds, experimentally, of rolling them when you added. So we're like, okay, well that's interesting, but why might that be? And in really every class, there were a couple people that started talking about combinations. It's easier to get a 7 because there are many more combinations that are going to give you a 7 than it would be to get you a 1, well that's impossible, or a 2. So some people were noticing that in order to get a 2, you would have to have a 1 and a 1. And that's the only way you can get it. But to get a 3, you could get a 1 and a 2, or you could get a 2 and a 1. And they kind of went up like this. And then on the other side of things, to get a 12, the only way of getting that was a 6 and a 6. So it looks like there are less opportunities. But looking at this, I was like, yeah, but how are you going to make sure that you've got all combinations? That looks like it could get tedious, and you might also forget something. You might miss a combination. So I encouraged everybody to look at tables as a way that we can organize ourselves really clearly. We set up a table that had each die roll on one of the axes. So let's say that this row is our first die, and I can roll anything in the sample space, 1 through 6. So this would be die 1. And on my second die, I can also roll anything 1 through 6. So this would be die 2. And if I'm going to be adding the 2 together, I can, using this, get every single possible combination. And you get to see how good I am at drawing lines. Right away, I can see how many total possible combinations there are, because I have a 6 by 6 array. So altogether, there are 36 possible outcomes. But they're not all 36 different things, like people started noticing. There were different ways that you could get certain numbers, so some things are going to come up in certain ways. So 1 and 1 gets me 2. There is no other way to get 2 on here. No. 1 plus 2 would give me 3, 4, 5, 6, 7. 2 plus 1, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. Starting to notice some nice diagonals. 5, 6, 7, 8, 9, 10. I can predict these is going to be 6, 7, 8, 9, 10, 11. And if I did 1 plus 6, just to check in, 7, 8, 9, 10, 11, 12. So there's only the one way to get a 2. Down here, there's only the one way to get a 12. I can use this to find the theoretical probability of rolling any of the numbers between 2 and 12, because I can see how many possible ways are there that I could make it out of all of the possibilities. So if I were talking about the theoretical probability of rolling a 2, and I'm just going to shorthand that as TP of a 2, that would be 1 out of 36, because there's only one way to do it out of 36. If I wanted to do the theoretical probability of rolling a 3, I would find my 3's, and they are arranged for me already. So there are 2 out of 36, or 1 out of 18. If I wanted to look at my probability of rolling a 4, theoretical probability of rolling a 4, that would be 3 out of 36, or 1 out of 12. And going through this, I can see that my theoretical probabilities are not all the same. So this ends up not being fair in that if you had put your piece on something that said 2, you only had 1 chance out of 36. And if you had yours on something like 7, you have 6 chances out of 36. You have a much better probability of landing on a 7 than you would of landing on a 2. I can also use this to think about things beyond individual numbers, and this is what people did with their in-class practice today. What if I wanted to think about the odds of getting an even number? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of 36, which makes sense. I'm kind of hopping up each time, which would be 1/2. If I wanted something that was divisible by 5, then I would look for everything that has 5, so 5's, 1, 2, 3, 4, and anything else divisible by 5, so 10. 10 divided by 5 is 2. So I already had 4, 5, 6, 7, which would be 7 out of 36. And then because I asked you guys about perfect squares, a square is any number that can be made that is the product of 2 identical numbers. So something squared equals 4, for example. That would be a perfect square. Or something squared equals 9. That would be a perfect square. Well, we have 2 times 2 is 4, 3 times 3 is 9. How about 1 times 1? That's 1. But we have 4 times 4, that's 16. We don't have any 16s on here. So we're going to look for our 1s, 4s, and 9s. We don't have any 1s on here. So I have 1, 2, 3, 3 4s. And I have 1, 2, 3, 4 9s. So 3 plus 4 would be 7 out of 36 would be my odds. I'm looking for all of the possible combinations that are going to make whatever that desired outcome is. This works if you're adding 2 things together. You've got an addition table like this. Works if you're multiplying. Might start feeling like a multiplication table. It works if you're combining anything in any way. So taking a look at the practice, we had the in-class practice. We were looking at eyes and eye color for some aliens. So this is getting into genetics. So what if you could have 2 eyes or you could have 3 eyes? And the odds of this are 1/2 and 1/2 because we have the 2 and they're equally likely. Or you could have purple eyes, and you could have purple eyes, or you could have blue eyes. And the odds of each of those are 1/2 and 1/2. This is like that Punnett square. In this, the combination of 2 eyes and purple eyes would be having 2 purple eyes. Combination of having 3 eyes and purple eyes would having 3 purple eyes. The combination of 2 eyes and blue eyes would be 2 blue eyes. And of 3 eyes and blue eyes would be 3 blue eyes. Now, if I asked about the theoretical probability of having 2 purple eyes, I would find what outcome here matches that. So 2 purple eyes, only 1 out of the 4 possibilities. That would be 1/4. What if I wanted the theoretical probability of having 2 eyes, and that's all I'm interested in? I would look for anything that says 2 eyes, 2 purple or 2 blue eyes. That's going to be 2 out of 4, or 1/2. Theoretical probability of having 4 eyes. There is nothing with 4 eyes on here, so it would be 0 out of 4, or 0% probability. So I guess none of these guys have classes. So we're going to be looking at other ways to organize these events that we call compound, and we're going to talk more about being compound tomorrow. But when you have two or more things that you are putting together and looking at the odds of the combinations that you're going to get, having some way to really clearly organize yourself, like a table, as we did today, is going to be really helpful because then you know you have all of the possible combinations. Have a good night. I'll talk to you tomorrow.